Okay. Hello, and thank you all for joining us today. It's really an honor to have you here, and for me, to be honest, to be here myself. I'm Bren Worth. I'm the CTO of Substrate AI, and I've been joined with Dr. Mei Si from Rensselaer Polytechnic University in New York. And we're here to talk today about our integrated multitask agent with affective light guided behavior. And next. May.
Yes. Hi, everyone. Welcome. And I'm really honored to be here and introduce this work. So as you know, in recent years, pretty much after 2013, I would say 13 as the beginning year, but 15 is really when machine learning algorithm get really popular. And a lot of things that we didn't expect to see before start to emerge. And things come out really, really fast. So I think the first significant event was in 2015 when AlphaGo was able to beat human player in Go. So for people who are like in the area of AI, or if you play Go, this is actually a very significant event. Before this happened, not many people, even for AI researchers, not many of us can actually imagine this can happen. Actually, for many years before that, we thought, not me in particular, but many researchers thought Go is a complex system that represents something that definitely needs human cognition and has often been used as an example to illustrate the difference between machine intelligence and human intelligence. So if you listen to the recent podcast, David Silver, who worked at DeepMind and who worked on this AlphaGo work, he had a recent interview with Lex Freeman. He actually talked about this process. So it was really exciting when this news came out, and things become even more exciting 2 years later when AlphaZero came out. In AlphaGo, at least, right, the AI algorithm played with human record of playing Go for many, many years and learned from those records. In 2017, when AlphaZero came out, this algorithm played with human the first time when they start a match. So in other words, it has never played with people before. So what it has been trained for, or what it has been played with, it played with itself using an algorithm or a method called self-play. So basically just two AI agents compete with themselves. And AlphaZero has even more impressive performance than AlphaGo. I think it won the human player in the very first match. And then the designer decided probably we don't need AlphaZero to be there to beat more human players, and let's move to other areas. So both of those events are quite shocking, and both of them happened in the general area of AI and in a very specific corner of the algorithm called reinforcement learning, which is also the algorithm that we are working on. So after 2017, this movement in continuously developing more powerful reinforcement learning algorithm didn't stop. In 2018, the company OpenAI, I'm not sure how many of you here are gamers and play Dota, but just for your information, Dota is a massive multiplayer game with strategies and coordinations between team members. So it's considered very complex. Dota, in a way, it's even more complex than Go, if you read about people's comments and explanations on that. So even after AlphaGo and AlphaZero, still for those of us who worked in games, we thought, okay, especially with Dota, right, you have to process real-time image information. We thought that's just way more too complex for AI algorithm. But then again, it happened. In 2018, OpenAI trained their reinforcement learning agents called Dota 5. That's the name of their agents because you need 5 agents for a team. They beat human players professionally in Dota. And 2019, this is a very interesting video I didn't include in this talk. OpenAI, again, had their trained AI reinforcement learning agent developed very high-level strategic collaborations in a demonstration environment called hide and seek. So as you can imagine, one group of agents is trying to hide themselves from another, and then in this process, they need to use props. They move objects around, build shelters, and then the other group of agents have to try to crack the shelter and reach to this group who is hiding. So in this process, their reinforcement learning agents demonstrated very high level of intelligence in collaborating, in utilizing the objects in the environment, and also in collaborating with their teammates, which is an ability that we used to believe only human beings have. And then 2019, later in that year, again, DeepMind created StarCraft 2 AI, which beats human players in StarCraft. So the image I included to the right, that's sort of like, I know the image is a little bit blurry, I'm not sure how it looks on your larger screen, but that basically shows like how the AI performs in comparison to human performance. So by the year of 2019, when DeepMind published their AlphaStar, this agent can beat 99% of human players in StarCraft, which is also huge. So next. So in all of those achievements I just talked about, they all utilized this algorithm called reinforcement learning. Again, so what is reinforcement learning? It's just an AI agent tries to learn about what it should do given a certain status of the environment. So it looks at, or in AI world, we call that observations. It observes what happens in the world and internally model that as state of the world. So the state is, for example, agent A is at location XY, agent B is at location X2, Y2, and agent B is in addition not healthy, such and such. So in observing all of this collaborative environment, information about the environment, about the agents, both your team members and other members of maybe in the opponent's team, the agent collect all of this information and make a decision based on the state. Of course, this process doesn't happen magically. It happens through iterative training of adjusting basically an estimation of a value function for, given the current state, if I take this action, what is its value? Is it better than taking alternative action? And this process is achieved through iterations and iterations. So all of the reinforcement learning agents in general, or all of this family of algorithms in general, takes a very long time to train themselves, which is the process, again, to learn about this mapping of value function for taking action for different various state of the environment. So this family of algorithm, have they been used? Where have they been applied? We've seen a lot of application of those in games. And of course, the company, right, training such algorithm is very expensive. To just give you example, I think the algorithm OpenAI used to play Dota 2 is a more recent version of reinforcement learning. It's called PPO. PPO is actually the last. I was about to tell you that this algorithm have also been used for stock trading exercise. I call them exercise because they don't work that well, at least not working as well as the system that we're going to present today. But so one variation of the AI algorithm that was created for playing Dota was this last one I listed on the slide, PPO, which stands for Proximal Policy Optimization. In this algorithm for playing Dota 2, I think they just train continuously year-round. And each day they need to involve 256 GPUs, as well as, I think, a couple of hundreds of CPUs. So actually, I think the estimated cost for training this model was something around 30 million, or I could be wrong. I don't have that number written down on my notes. But it's a huge amount of money for training such an agent. So this development is significant, and people have tried to apply this agents to other fields, language generation, healthcare, and of course, people have thought about using such agents to do stock trading automatically. So throughout the years, many of the reinforcement learning agents has been used for stock trading. So I just listed some of the alternatives here, including PPO, which is the one that have received huge success in Dota and in StarCraft. The other two algorithms I listed here, the A2C, A3C, which stands for Advantage Actor Critic, and Deep Determinist Policy Gradient, DDPG, they have also achieved a lot of success. Not in the games area, unfortunately, or fortunately, but that's partially why they're sort of less popular than PPO. Regardless, they all have benchmarked great performance comparing to the very basic version of reinforcement learning, and they all had a lot of success in other fields, but yet they don't perform that well in stock trading. Stock trading is a different problem. Next. So I want to talk about the motivation for us to bring reinforcement learning and why we want to invent this particular version of reinforcement learning agent to do stock trading. So a lot of work has been done in improving the performance of reinforcement learning agents. Most of the improvements so far, including the PPO, the DDPG, the A2C I listed in the previous slides, most of them look at the mathematical aspect of the computation itself and try to make the computation more efficient from the mathematical angle. So for example, the PPO agent, what it tries to improve over the very vanilla reinforcement learning agents called Q-learning agents. So what PPO try to do is it tries to restrict how gradient, so all of this agent, because you have to train the neural network, there's a gradient descent process, you have to calculate the gradient. So PPO tried to improve upon the very vanilla Q-learning reinforcement learning agent by restrict how that gradient should be calculated. And as a matter of fact, PPO learns dramatically faster, more robust than Q-learning agent. But fundamentally, theoretically, all of those algorithms all come from this very intuitive thought or understanding about the world. Let's just try to map action, state of value of action to a particular state that we want to model about this world. And as you can imagine, for any of the problems, even the games problems, but also for the stock trading problem in particular, the state space is huge. It's really huge. So it would take a very, very long time for any of the reinforcement learning agents to train themselves to perform effectively in such environment. So that's a big bottleneck. The reality is, if we have enough time, enough computational resource, we can probably train any of this agent to perfection. But the reality, but then the truth is, nobody, right? Even major companies like OpenAI, nobody have that much resource. Training an agent with 256 GPUs for months, it's a lot of money. And then, so our angle to approach this problem is to look at humans. We don't have 200 GPUs, or maybe we have more. Of course, we have more neurons in our brain. But we try to look at how the human cognitive and affective systems work together to, well, I guess we don't solve problems, but we are really efficient. If you think about our humans as AI agents for machines, we're really efficient in, as a general purpose problem solver, to deal with different conditions and solve different problems. So our inspiration comes in by observing and knowing that in human, we don't just use logic to make decisions. So even for very serious decisions, there's always a room for our emotions and moods to kick in. And that emotion and mood, they're not something that just makes you moody, right? They're not something that is against rationality. They're something quite fundamental to our cognitive system that allows us to make better decisions, that allows us to adapt better for the environment. So in this work, we try to simulate or mimic that process in our computational system by modeling emotion and affective signals and let that signal participate in the agent's reinforcement learning agent's process of selecting its intrinsic goals, pay attention to relevant signals in the environment, pay attention to relevant signal internally, and to decide or like a pre-filtering of what actions are more relevant to the current state. Next. Just to readdress this emotion as an integral part of our cognition point a little bit. So even like I just mentioned, even for very serious decision making, emotion always play a role. So emotion, if you're familiar with how our brain is developed, actually the part amygdala so the part of the brain that is related to emotion experience and emotional driven reactions are developed first in human brain. And so the same for animals, at least mammals as well. So those part of the brain is called the old brain. And then when the frontal cortex is developed, we call that the new brain. So the frontal cortex is mostly, as you may know, that they do more of our so-called rational thinking partially by inhibit some of the reactions, but also interact with the reactions and signal from the old brain. So what exactly does the emotional related so-called old brain do to our mammals and humans, at least to this state? They basically they basically prepare. So the emotion and mood, they sort of unconsciously prepare a action tendency for human to react to the environment. Whether it's a risky environment, you should really get yourself ready and flee, or it's an environment that you should fight. So that's just a simple mapping to like when old times when we still physically fight. But the same concept can transfer over to like social interactions and social environment. It also, emotion channels your attention in humans. I'm not talking about for agents, but emotion channels your attention to the type of stimulus or information in the environment that are most relevant to your current task. It coordinates by channeling your attention. It actually also affects how you utilize those attention, how you rational decision making process are laid out based on those attention. So of course, emotion, which this is a little bit beyond this talk, but emotion in general also have the role of bonding us to each other, build social groups. If you think about like typical emotions such as empathy or guilt, that's very social oriented. But even without the social oriented components, the individual reaction or experience of emotion still takes the role of helping us to see the world in a way that is shaped by our emotion and word and emotion and mood, and also it shapes the way that we process information, utilize information for making decisions. As a cognitive scientist, we believe that this process is evolved through human evolution to enable human beings to utilize information more efficiently. Because even though human brain has a lot of potential capacity, the stimuli, the amount of information around us are still too much for human brain to process. Therefore, at least process all at once. Therefore, the emotion mechanism acts as a filter and a regulator to enable human cognitive systems to utilize information more effectively. Next. So how does this all link to the computational process for this reinforcement learning agent that we're building? We basically try to mimic the process and we model emotion as so just like how human emotions are triggered by environmental stimuli, we model emotion of this treating agent by the reward and the speed of change of reward the agent receives. So we allow this emotion signal to channel in to this agent's selective attention to its state or to the environment state, and for the agent to select sub-goals that receive priority to be taken care of. Also, the emotion channels in to let the agent pre-select actions. Certain actions are not relevant or less relevant for the current circumstance of the environment. So this operation, similarly as how human beings are benefited from having an effective system, this operation overall reduce the computational cost for our reinforcement learning agent to operate as well. So more specifically, down to the computational level, we implement as a multi-agent, actually multitask system. We implement the different effective regulation process, such as how emotion participate in goal selection process. We model all of the sub-process as separate reinforcement learning process. Actually, we model all of those as a separate Q-learning process. And then we integrate all of those systems together. They cooperate and co-evolve as the overall agent system interact with the environment, in our case, interact with data. We have some experimental results as well as, of course, practical results of applying this agent to real trading scenario and other machine learning scenario to demonstrate the success of this agent. Next, and I think I can hand this over to Brent.
Thank you, May. So we've had some background and we've had some motivation. The question is how do we actually build an agent that possesses these particular qualities that we've just recently talked about? So to do that, as we May had mentioned, we've broken out the problem of the agent into different submodels, as seen here, where the arousal and the emotive model represent the emotional subsystem. The goal model, the attentional model, and the affordance models represent kind of the behavior guidance and restriction, like inhibition, that we had talked about just a moment ago. All this is used as input into our experiential model, which is actually responsible for interacting with the environment, where the output from the action from the experiential model is then verified, or I guess masked, to ensure that it's actually within the allowable action space selected by the affordance model, which is part of our impulse control model, and has been shown to be very critical in the improvement of our trading models, specifically around creating highly risk-adjusted returned models, high Sharpe ratio stock portfolios. So the affective subsystem, as I mentioned, is composed of actually two models, the arousal and the emotive system. These models are based on a simple concept of emotion. In this case, it's the first and second derivative of the change in value that the agent receives over time. This was used to be able to create a simple representation by which we can say the agent is either in a good state or in a bad state, and that state is getting worse in a more rapid or slower way. How should I say? I'm going to move on to the next part. Sorry. So the goal learning model takes in the effect of the emotional input from the subsystem and selects a state from its prior experiences as a sub-goal, creating like a breadcrumb type trail of different states in which are ideal for the agent to get into, such as, let's say it's dealing with a threat environment where you've encountered a rattlesnake on a trail. So in this case, a sub-goal could be different parts of the trail that lead away from the snake, not towards the snake. To do this, we use just a simple iterative system here. But however, in the future, we anticipate actually working on a hierarchical states, which is actually a significantly smaller state base and much more practical for larger problems. But that's for subject for future work. The selective attention operates by identifying what features are relevant for a particular context. In this case, let's say with the snake environment, where you see the rattlesnake, so you orient to the rattlesnake, but then you also identify what parts of the state space actually could lead you away from this particular threatening environment. So these are the features in the state space, not the rest of the state space, the trees, a big boulder to your right. These things are ignored, and prioritized are the parts that are the threat and the parts that allow you to escape. To do this, we actually represent the state value as just an integer value, which we iterate up and down. And then what we do is we convert that to a state binary mask, which is then ANDed with our actual features that we get from the environment. This leads us to a reduced state feature collection, which is inputted into our experiential model to make reasoning on. So action affordance has played a critical role, as I mentioned, in our financial models, which is different than actually, let's say, the Go game, where risk actually in risk-taking behavior needed to be modulated because while greedy actions or a perceived expectation or perceived knowledge of a trading strategy doesn't always remain true over time. So in this case, we use the emotions to allow it to be able to select and then figure out what actions it shouldn't be taking, given the fact that it might be too risky to take that buying the stock or selling the stock in a case where it's actually diving. When if we were to hold on to those stocks a little bit more, they would rise and you'd have a positive profit on that. This works in a similar way as our attentional masking system, where we have an integer value that represents a state for the affordance. And we convert that into a binary representation, which is ANDed with your action space. In this particular instance, we're working with discrete action spaces only, but we've worked on some ideas to generalize this to more continuous action spaces. And the output of this is the only active state actions that an agent can perform within a particular context. Okay, so we put this all together. We have an emotional subsystem that generates a strategy based on how the agent is receiving value from the environment. So it can be in the same environment, but get different kind of value over time. So it develops different strategies, which narrow down the different things that an agent can do in the environment by creating a breadcrumb of local goals for a particular strategy that are then identify what features are important to that particular goal. Okay, in this case, moving away from the rattlesnake. Okay, so we know where the rattlesnake is, and we know where the trail that gets away from that rattlesnake is as well. And our affordance model makes sure it keeps us from doing something stupid, something that could be more useful in like social contexts. Depending on alcohol, this can be better or less controlled. And all this is actually fed into our experiential model, okay, where we update the state feature to represent only the features that the states should be focused on. We enhance this state that the experiential model sees to include the rest of the arousal, the emotional system, the other intrinsic model outputs that we have, and then generates an action output from this. And this action output is then verified that it's within the set of available actions based on the affordance model. So we experimented with this. Our main experiment was actually our trading activities, but we wanted to do a larger test over a different kind of game than we do for financial trading, using a vanilla Q-learning agent that is actually our agent is actually built on top of. So they're identical technologies from the very basic. Okay, we created a 10-game series with a 5x5 board, and each game series executed 500 games. We've actually redone this experiment with 3,000 games to verify these results, and we also got the same results from that size of data training, I should say. And we use identical hyperparameters for both our IMT model and the Q-learning model. And the win-loss ratio is excess of 20% for our IMT agent, with an excess of 700% long-term cumulative Q value. So significantly more efficient use of learning or generating of learned behavior by our agent. So what do you want to think? So our current ideas here is that we've been able to demonstrate this in both a test environment, but also in real life, where we're actually in the top 2 and top 5% in performance on the Collective 2 trading platform, which is primarily traded by humans. So I don't know if it's not exactly a direct comparison, but we've definitely performed very well on that environment. We've also built a model for use of our AgTech product for identifying feed and supplements to be used in milking for goat farms, commercial milk farms using only 3 months worth of data, and we're able to achieve results in 70% accuracy based on the recommendations of a professional vet. And actually, there was some other additional challenges with real-world application there, but needless to say, we're able to apply the agent and actually be able to make it work. In the future, we anticipate applying some new enhancements to our core algorithms, a lot of it to increase the ability to scale, using some recommendation technologies maybe to improve in it. Also adding some of our newer technologies around hierarchical RL and options learning, which is kind of like reusable skills, as well as kind of like maybe some prefrontal lobe kind of technologies in the future. We also wanted to do some ablation studies to kind of understand, kind of like a breakdown, why is the agent performing the way it is? And it's not entirely clear at this point in time. So we're going to basically break the whole agent down, see how different parts perform on the same test example, and kind of get a better understanding of the contributions from each of our models in our subsystem. And we also want to explore maybe a more tightly coupling with affect in our model. So right now, it generates kind of like an extended state features, but maybe that we can include this to be able to actually update different states in the goal model or other models in the hierarchy. Thank you. Is there any questions?
Hello. How long have you been working on the AI development that you saw us?
Sure. It's a great question. I've been working on that for close to 15 years now, since DeepMind came out with their paper on the topic. I saw their Nature paper and I was like, oh my God, I can do this. We could totally do this. So I immediately rounded up my philosopher friend. We went to a bar, drank a little bit, and got very creative with our ideas.
Hello, good afternoon. So my question is, I see from what you both have said, this is a very different model from the ones that are currently being used in life. So my question is, how did you reach to this point? What's the path that you follow in your brain to reach to this kind of model?
Sure. Actually, that wasn't an obvious direction, to be honest. Intuitively, I understood that emotions played a role in our decision-making process, and that it was involved with guiding our decision-making process. And my imagining was that it was about shaping and reducing the state space, because I know that the classic examples of trying to solve these AI problems is that you do like A-star search, just massive state spaces, and it's impractical to search them all. Okay, so I understood that my intuition was that emotion played a role, and actually it was kind of like accidental. I had some ideas about trying to shape how the decision-making process occurred, but it was actually when my laptop crashed and I had to re-implement the whole thing that I like, oh, wait a second, this all makes sense if you put it all together, and these are the different pieces, and I have a concept that could be like considered emotion. My philosopher friend, I called, and he was like, no, you don't have emotion. And we had another bar and drinking on that point too, to discuss the finer points.
Hi, Ren. Thank
Hello.
you very much. It's very nice to have you here. I would like to ask you, how will you apply the AI in the real world?
Sure. Actually, reinforcement learning is not often applied to real-world applications, mostly for a set of reasons, not just one, but a set. One, the agents can't, if you don't have a simulatable environment, you really can't deploy, especially in anything that's critical, like healthcare, for instance. You can't actually apply this you can't apply standard Q learning or reinforcement learning to application. Also, the real world is complex, and the human mind has actually learned or has structures that build abstractions that allow it to think better about the environment and to be able to plan in a way that's much more efficient than our current technology supports. And I think thirdly is I would say that the environments are not stationary. Okay, a lot of these technologies, like in the Q learning, they assume that the environment is going to, once you've converged to a solution that you understand that environment, that environment is always going to stay that way. Our technology actually doesn't make that assumption and has algorithms behind it to help it to be able to say, oh, you know what? I don't really think I know what's going on. Let me change the way I interact in that environment so I can actually learn more, or maybe take less for face value of the environment than I was.
Hi, Graham. It's Oscar here. Do you think in the future it will be possible to have variants from this architecture, but instead of being based on Q-learning, based, for example, on actor critic?
I'm sorry, say it again. I didn't hear quite.
Instead of being based on Q-learning, based on actor critic models?
Absolutely. Actually, to be honest, the algorithm could be built on top of any of these technologies that may the DDPG, the PPPO, TRPG, the trusted. Man, I forgot what the whole acronym is, but yes, there is absolutely nothing that prevents us from implementing on top of that. And actually, there's some brand new work that we built prototypes for that's coming out soon, that is in more of a distributed cloud type of structure that also can support different technologies as well. But that's for a future paper, hopefully in the next month or two. Good question.
Any other question? Great.
Thank you, everyone, for coming. Thank you, May.
Thanks.
And I think goodbye. You can disconnect now, May.
Okay.
Excellent.